Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in previous lecture we have started last unit of this paper. So we have started unit number 4, that is queening theory. So in previous lecture we have seen some introduction part about the queuing theory. We have seen queuing system. Okay, so we have seen also some characteristic of the queuing theory. Okay, so in this lecture we will see pure birth and death process of the model. Okay, so in previous lecture we have seen total 5 points of the queuing theory. So in this lecture we will see a next point, that is point number 6, probability distribution in queuing system. Okay, so before going to start pure birth process, we will see 3 axioms which are very most important to uh, to show that to prove the pure birth process. Okay, so in probability distribution queuing system, the customer will come in a random manner and that will follow the Poisson distribution. Okay, so in generally the service times are assumed to be exponential distribution. Okay, so queuing system generally depends on following three axioms. So axioms number 1 is the number of arrivals in a non-overlapping intervals are statistically independent. That is, the process has independent increments. Second axiom is the probability of the more than one arrival between time t and time t plus delta t is O delta t. Okay, that is the probability of two or more arrivals during the small time interval delta t is negligible. Thus, P0 of delta t plus P1 delta t plus O delta t equal to 1, or we can say that the order of delta t. So, this notation will be given as limit delta t tends to 0 sigma delta t upon delta t equal to 0, or for the understanding we will call this letter, that is order of delta t. Okay, for the purpose of understanding. Third axiom is the probability that arrival occurs between time t and the time t plus delta t. So t plus delta t is a change increment in time is equal to lambda delta t plus order of delta t, and which is given as p1 delta t equal to lambda delta t plus order of delta t. So from this axiom number 2 and 3, here lambda is a constant and which is independent of the total number of arrivals up to the time t, and delta t, so these are the notation, delta t is an increment element, and here order of delta t which represent the terms such that limit delta t tends to 0 sigma delta t upon delta t equal to 0. Okay, generally in our unit we will call as the order of delta t for the understanding. Okay, now we will see the first model, that is distribution of arrivals, or it is called as a pure birth process. Pure birth process. So in this model the arrivals are counted and no departure takes place, and it is called as the pure birth models. Okay, what is the definition of the pure birth process? The model in which only arrivals are counted and no departure takes place are called pure birth models. Okay, so in this model only the arrivals will be count and no departure will be uh, cannot be count. Okay, so that is called as a pure birth process. So stated in terms of queuing, birth death process usually arises when the additional customers increases the arrivals referred as birth. In the system, the decreases by the departure referred as death of the service customer from the system. Okay. So suppose that there are the arrivals persons, so that is called as a birth. It is called as a birth. And suppose there are the persons, the system is decreased by the departures, so that is called as a death. Okay, death process. Okay, death model. So what is the probability of the persons to come into the system? Okay, now we will show. Now we will see the pure birth process. So let us suppose that Pn of t denotes the probability of the n arrivals. N arrivals means these are the number of persons in a time interval of the length t. So let us consider t with the time interval, that is t, both waiting and in a service. So this is the time those persons who are waiting in a queue and also taking a service in service, where n greater than equal to 0. Okay, so always n greater than equal to 0 is an integer. So n, which represent the number of persons, number of arrival person. So then Pn t plus delta t being the probability of n arrivals in a time interval of the t plus delta t. So t plus delta t means change in time. Okay, so change in time. So making use of axiom number 1. Okay, now we will make the differential equation. Okay, difference equation. So by using axiom number 1, so Pn t plus delta t probability of time change, the probability of the persons who are coming in uh, time changing. Okay, so Pn t plus delta t equal to, the difference equation can be written as P of n arrivals in a time t and one arrival in a time delta t. Okay, number of persons in n arrivals in time t and one arrivals in delta t. Delta t means increment in time, plus probability of n minus 1 arrivals in a time t and 1 arrivals in a time delta t, plus probability of n minus 2 arrivals in a time t and 2 arrivals in a time delta t, and so on. In this way we can write probability of no arrivals in a time t and n arrivals in delta t for n greater than equal to 1. Okay, so here n is greater than equal to 1. N means number of person. The number of person will be 1 or more than 1. Okay. So by using the axioms number 2 and axioms number 3, the difference equation can be reduced into the following form, and which is written as Pn of t plus delta t equal to the mathematical form of these axioms number 2 and is in axiom number 3. Pn of t plus delta t equal to Pn of t P0 of delta t plus Pn minus 1 of t plus P1 delta t plus order of delta t, and which is written as Pn of t equal to, so P0 of delta t, that is 1 minus lambda delta t minus order of delta t, plus Pn minus 1 of t as it is, and P1 of delta t, which is written as lambda delta t plus order of delta t, and this order of delta t is as it is. Okay. So here the last term. So here the last term which represent the terms, that is probability of n minus k arrivals in a time t and k arrivals in a time t. Okay. So where k is 2 less than, where k lies between 2 to n. Okay, 2 to n. The above equations can be, this equation can be rewritten as Pn of t plus delta t minus Pn of t. So taking, interchanging or taking in left hand side after solving this term. So we will get minus lambda delta t into Pn of t plus lambda delta t Pn minus 1 of t plus order of delta t. After simplification we will get on this step. Okay. Now we will divide on both side by delta t. Okay, and taking the limit delta t tends to 0. Okay, so after dividing delta t on both side and taking the limit delta t tends to 0 on both side, then the above differential equation, then the above equations can be written as, can be reduces in the following form, that is the dd of dt pn of t, dd of dt pn of t equal to minus lambda pn of t plus lambda pn minus 1 of t. Okay, so here n is greater than equal to 1 for the person, where n is the number of the person. Okay, n greater than equal to 1. Okay, now suppose n equal to 0, suppose n equal to 0, no person will arrive for n equal to 0. So this can be written as p0 t plus delta t, p0 of t, p0 of delta t. Okay, so which is equal to p0 of t 1 minus lambda delta t minus order of delta t. P0 of delta t means 1 minus lambda delta t minus order of delta t by the axioms number 1 and 2, 2 and 3. Okay, so after rearranging, okay, after solving these steps, after solving this term, okay, and dividing on both sides delta t and taking delta t tends to 0, okay, and after solving we will get dd of dt p0 of t equal to minus lambda p0 of t. So let us consider equation number b, and this is equation number 1a. Okay, so in this way we can obtain the differential equation. Okay, so using equation number a and b, okay, using equation number a and b, we will solve this n plus 1 differential equations in equation number a and b. So here we will use the generating function, that is phi zeta phi z of phi of z comma t equal to summation n equal to 0 to infinity pn of t z to the power n. Okay, in a unit circle mod z less than equal to 1. Okay, we will use this probability generating function. Now multiplying the differential equations in equation number b and a by z0, z1, z2, z3 and zn respectively, and taking the summation over the n from 0 to infinity. Okay, after solving the differential equation a and b, we will get a summation n equal to 0 to infinity dd of dt pn of t z to the power n, which is equal to minus lambda phi of z comma t plus lambda z phi of z comma t. Okay, so this can be, so after solving this equation can be written as, or it will give us dd of dt phi of z comma t equal to lambda z minus 1 phi of z comma t. Okay, so after solving, the above differential equation can be reduced in the following form, that is phi of z comma t equal to c e raised to power lambda z minus t z minus 1, okay, into t. Okay, so here c is a arbitrary constant. To determine the arbitrary constant c, we will use the initial conditions. There is no arrival by the time t, so t equal to 0, then we will get, so put t equal to 0, so phi of z comma 0 p0 of 0 plus summation n equal to 1 to infinity p n of 0 z to the power n equal to 1. Okay, so here we will get phi z of 0 is, that is equal to 1. So now p n of 0 equal to 0 for n greater than equal to 1. So therefore we will get c equal to 1. So putting c equal to 1 in this equation, we will get this equation, that is phi z of t equal to e raised to power lambda z minus 1 of t, equation number c. Okay. Now we will uh, take the differentiation with respect to z to equation number 1. Now differentiate with respect to z to this equation number c at a point z equal to 0. So phi of z comma t at a point z equal to 0, we will get p1 of t. Second derivative, that is d square dz square phi z of t at z equal to 0, we will get 2 factorial p2 of t. So in this way, the n derivative of this term, that is phi of z comma t equal to at z equal to 0. So we will get n factorial Pn of t. Okay. So using the value of phi z of t in equation number C, we will get P0 of t equal to e raised to power minus lambda t. Second, P1 of t equal to lambda t e raised to power minus lambda t. P2 of t equal to 1 upon 2 factorial lambda t e raised to power minus lambda t, and last term Pn of t equal to 1 upon n factorial lambda t to the power n e raised to power minus lambda t. Okay, so therefore the general formula of the pure birth model is written as Pn of t equal to lambda t to the power n upon n factorial e raised to power minus lambda t for n greater than equal to 0. Okay. So this formula is known as Poisson probability law with mean lambda t. Okay, so this is also called as a Poisson probability law with mean lambda t. Thus, the random variable defined as the number of the arrivals to the system in a time t has the Poisson distribution with a mean lambda t arrivals or a mean arrivals rate of lambda. Okay. So this is the first model of the queuing system, that is a pure birth process model. Okay. So in next lecture we will see the second model of this uh, point. Okay, that is a second. Okay, so we will see the second model, that is distribution of inter arrival times, that is exponential process. Okay. So we will see in briefly. Okay. So inter arrival times are defined as the time intervals between two successive arrivals. Okay. So in this distribution of inter arrivals, so this will follow the Poisson distribution in associated with random variables defined as the time between successive arrivals, that is the inter arrivals time, follows the exponential distribution, and which is given as f of t equal to lambda e raised to power minus lambda t and vice versa. Let the random variable capital T be the time between successive arrivals, then we will get probability of t greater than t equal to p. No arrival, probability of no arrivals in time t, so which is equal to p0 of t equal to e raised to power minus lambda t. We know that p0 of t, that is e raised to power minus lambda t. Therefore, the commutative distribution function of t denoted by f of t, and which is given as f of t equal to probability of t less than equal to t equal to 1 minus probability of capital T greater than t, and which is equal to 1 minus p0 of t, and we know that p0 of t, that is e raised to power minus lambda t. So therefore 1 minus e raised to power minus lambda t, t greater than 0. Therefore, the density function f of t of the inter arrival times is given as f of t equal to dt of dt f of t, capital F of t equal to lambda e raised to power minus lambda t, t greater than 0. So hence the expected mean or inter arrival time is given by e of t equal to integral 0 to infinity t into f of t dt, which is equal to 0 to infinity. We know that f of t is t e raised to power minus lambda t dt. After solving this integral, we will get 1 upon lambda. Okay. So here lambda is the mean arrival time, mean arrival rate. Thus, the capital T has a exponential distribution with a mean 1 upon lambda. We would intuitively accept that if the mean arrival rate is lambda, then the mean time between arrivals is 1 upon lambda. Conversely, we can also show that if the inter-arrival times are independent, then and have the some exponential distribution, then the arrival rate follows the Poisson distribution. Okay. So here we have seen two models, that is first is pure birth model and second is the exponential process model. Okay. So in next lecture we will see the third model, that is a pure death process model. Okay, so in next lecture we will see the third model.